Hi, welcome to the Calculus 3 lecture series. We are still in the unit about the multiple integrals, and this is our lecture number 4. And in this lecture, we're going to cover the surface area, how to find the surface area in R3. So if you give me like a function z equal to the f of x, y, and I have like the certain surface in R3. So how do I find the surface areas here? Okay, so now let's go ahead and take a look at what is our lecture notes about and how to find the surface area. And before we find the surface area, this is very similar like what we learned in the calculus 2 here. So I'm going to do a very brief kind of the review in the calculus 2. Then you can use the same ideas, right? Okay, so let's take a look in the calculus 2. Okay, so in the calculus 2, and so we learn how to find the what? Arc length. Okay, so what is the I means here? So I means here, so for examples here, if you give me a function here, right? So this is my f of x function. And then I have my a and the b's here, all right? So this is a and this is a b. And I like to know what is the length for this curve in between these 2 points. That's why we said the arc length here, right? Okay, so if you guys still remember, okay, so the formulas here is like, the formulas here, we say the arc length is here, is the integration of a and b, and then inside here, it says 1 plus f prime x to the square, right? So this is f prime x to the square, and then the dx is here. So how do we do that? And so let me get rid of this red one. Oh, good boys, I killed both of the color. Okay, that's fine. Okay, so if this is the one, I want to find the area between, I want to find the arc length between these 2 points. So if you remember in the calculus 2, we said, how do we find it? We still use the same like Riemann sum. So we say, hey, we got to just go to get the few points, right? Then we're going to use this, the length of the line segments, and try to predict. So like if this is my P0, this is my P1, this is my P3, this is my P4. So it's very similar idea about the Riemann sum, how to find the areas, right? So right now, I'm just divided this curve into 4 line segments. So I can use the length of the line segments to approximate the length of these curves here. Of course, the same idea, if I let the length go, if I let those p getting into like many small pieces, when n approach to infinity, then the line segments will be very close to the true length about these curves, right? Okay, so let's take a look. How do I get the lengths here? All right, so that's why we say by the Riemann sum concept, we know the limits, the length of these curves will be equal to the limit n approach to infinity summations I from 1 to n, and the length of the pi minus 1 and the pi's, right? So when you put the 2 points together, you got the segment of the length is here. Okay, so now let's take a look at what is the pi minus 1. So the pi minus 1, this is a pointer, so I know this point is x minus 1, yi minus 1, And the PIs here is the point what xi and the yi's here, right? So in order to find the line segments, we know the distance. How do I find the 2 points here? Will just be what? Will just be the xi minus xi minus 1 to the square plus yi minus yi minus 1 to the squares, right? And then from here, I know this is what I call this is the xi. So this is delta x. Then the point between here, right? So this difference is, we call it delta y here, right? So basically this is really, you can write this is delta x squared plus delta y squares, right? Okay, so now we also know, so by mean value theory, we know if the f of xi minus f of xi minus 1 here. So we said, hey, by mean value theory, we know there exists some xi stars here. So such that f prime xi star will times xi minus 1 will be equal to the differences here. So that's why we know these differences, this is what we call it delta y. So will be equal to what? F prime xi star and times x delta xi, right? So now it's kind of like makes sense now. So from here, right? So in here we can say, okay, so this is delta x squared. So what is delta y here? The delta y is f prime x and the delta x, the whole thing squares, right? So now you can take the delta x out. So that's why you get this is 1 plus f prime x and what is delta x. So that's how do we know the length here, right? So this is just like one line segments. So by the Riemann sum, if you divide it into many, so you add them together, will be equal to this curve. So when you sum, then when the n approach to infinity, become integrations, right? So this is what we did in the calculus 2. So why is this will help to understand how do I find the surface area for the, for curves here. So like if z is equal to the f of xy here, right? So we know in here, if this is your x, this is y, and this is z here. So then you have some type of the curve going on top of here, right? So how do I find if you have like certain boundary you want to find? So how do I find the surface area of this curve? And how do I do that? Okay, so it's still, okay, so if you take a look, this one's here. So this is the, for example, this is the, okay, the blue area is the curve, is the surface area I'm trying to find. So how do I do it? So instead of just so similar like the Riemann sum concept, I'm going to find a very small tangent plane, this pink ones here. This is the tangent planes here, right? So this tangent plane, if you cut it small enough, this tangent plane will be able to estimate the surface area of this blue one. It's just like in the Calc 2, you use the line segments, try to estimate the curves, right? So if you blow up this tangent plane, so you will see this tangent plane, you have A and B. So this is what we have here. This is what we have, it's delta J here, okay? So for the A, okay, so this is like in the x directions, right? So this is like, we said, this is a dx. And then this is what? This is dy here, okay? So from the, from the previous one, okay, so from the previous one, the Calc 2 here, so we know this line segments can be approximated by what? It's the delta. So this line segments is delta x and what? Expanded. So this segments will be the delta x and plus fx, the partial derivative of x here, and the times delta x, right? So in here, take a look, it's just like by the mean value series, right? So you kind of just take a look here, right? So that's what happens here. Okay, so now let's take a look at this ones here. So then the same ones here for the delta y's here, right? So the delta y, this line segments can be approximated by what? Delta y plus the partial and to the delta y's here. So I know also from the cross product, I know if you do the cross product, and then you take the length of this cross product, what is going to be? I know it's going to be the area of this parallelogram you're supposed to produce, right? Or it's the little square or rectangle you're supposed to produce. So for the A cross B's here, so I know this is the IJ case, right? So just like I would say, this one can be, this is from the previous slide we see here. This is the B's here, right? Okay, so this one, just put delta x, here is 0, then this is a partial fxy, then the delta x here, right? And then for the b's here, you put a 0 and the delta y's here, then f of y, xy, delta y, and then you do the cross product. And so I know this little area, the delta t area, okay, is equal to the A cross B. And if you figure that out, and so what is going to be here? So it's going to be it's going to be the square roots of what? F of partial xy to the square plus f of the y partial to the squares, and then plus 1, and the times the delta A, that's the small region, right? The small regions here. Okay, so that's why, so the areas here, right? So the total surface area will just be like we did it like the Riemann sum. You said the m and n approach to infinity, and the summations here, and I from 1 to n, j from 1 to n, then the delta Tij. So it will be just like you put all this together. And so when you put this together, so then when the limit approach to infinity, so what will be here will just be your integration over the regions here. If you, so this ones here will just be what? 1 plus f of x partial square plus f of the y partial square and the dA's here. All right, so that what is how we get this formula here is very, kind of derived from the using the Cat2, the arc length concept. So really, just like we did in the calculus 2, when we try to find the arc length, the hardest part is the integration itself. Because when you squares here inside, sometimes make the integration kind of difficult to do. But okay, so this concept is pretty easy, right? So it's kind of like very interesting, like when you do the Riemann sum, find the area. If you want to find the area under this surface, you use Riemann sum. Also, you use the rectangular prism to find the volume, and you add them together. So right now, I find the area of this blue surface. I use the tangent plane, try to approximate by using Riemann sum concept. Okay, so now let's take a look at some practice here. How do we do it? Okay, so first I want to find the area of the surface. X equal to the 3/2, x to 1. Okay, so x to 3/2 plus the square root of the 5 over 2 times y, and above these regions here. Okay, so this is my D regions, right? Okay, so the first things here, we know the formula, so we take the partial for x. So what is the partial for x? The power rule, 3/2, x equal to what? 1/2. Then y is a constant. Then partial for y, x is a constant. So what is the partial for y? Square root of the 5/2, see here. Then by plugging the formulas here, the area of the surface area. Okay, so here is like we said, here is what the here, all right, so this is 1 plus f of x squared, so it's 3/2 x to the 1/2 square, right? Then plus the square root of the 5/2 square, okay? So in here for this region, we need to be careful. You can integrate either one. So I will do the dy dx first. Okay, so the dy, that means I'm integrating along the y directions, right? So we said that the boundary has to match. So where is the y start? Y start at 0 and go where? Go to the 1 plus x here, right? Now, what is the finally, what is after you finish integrating the y, you try to find integrated x. So what is the boundary for x is from 0, 1, right? So be very careful here. And now let's take a look at what is the this integrations here. So these ones here, if you simplify a little bit, okay, so the inside here is 1 plus 5, so this is 1 plus 9/4 x plus 5/4, okay? Then you say you want to do dy dx here. Okay, so this one is 1 plus, so the 1 plus 9/4 dy dx here. So if you combine these two, so 0, 1, 0, 1 plus x here, it's not bad. So 1 plus 5/4 will give you 9/4 plus 9/4 x dy dx. Pretty cool. And then we have the 0, 1, 0, 1 plus x. I can factor the 9/4 out. So what I factored out is 3/2. So what is remaining in the x inside? 1 plus x dy dx. So I'm integrating y first. I can get rid of the, so I don't need to worry about the x terms here. So here this is 3/2. The x is a constant, so it's 1 plus x. Then dy, just the y, and then you put the upper bound and the lower bound, then you do the dx here, okay? All right, so this one turns out pretty cool. So when you put the y equal to the 1 plus x, so what is this one give you? So this one will give you, this is the 3/2, 1 plus x to the what? 3/2, right? dx here. Then this one will be pretty easy here. So this is the 3/2, and then this is the 3/2 plus 1, then this is 1 plus x, 3/2 plus 1, right? Okay, so now in here you have a 0 and a 1. So so this one here you simplify a little bit, it's 3/5. And if you put the upper bound and the lower bound, so it's 2/5 minus 1, 5/5, 5/2. Okay, so the final answer will be this is 5, and this is 12 square roots of the 2 minus 3. It's very kind of, it's just to try to show you how to do the regression, not regression, just show you how to do the integrations here. Thinking about the statistics. Okay, so this is just a very very mechanical integrations here. All right. Okay, let's take a look at the next ones here. So I want to find the area of the part of the surface z equal to 4 minus x squared minus, okay, so minus y squares, right? So when you do this, okay, so I'm looking for, this is my surface areas, right? Okay, so now the first things you take a look, see here, right? So this is, you know, this line, you know, this one's here, okay? This is the curve here. Right? For this curve, right? So this curve is z equal to 0. Am I right? Okay. So the z over equal to 0, that means 0 is equal to the 4 minus x minus y. So what I have here, I have x squared plus y squared equal to 4. So this is the circles, right? So when you try to integrate here, because x and y have a relation, you can either treat a, you know, integrate, treat x, or, you know, treat, you know, change the y to a function of x, or x to a function of the y. See here, right? So it doesn't matter. So in here, so I will try, so I said x is from 0 to 2. Then the y will be equal from the what? From 0 to 4 minus x squares, right? Square root of the 4 minus x squared. Okay, so now let's take a look. The partial of x. So what is the partial of x? Negative 2x, right? Then the partial of y. What is the partial of the y here? It's negative 2y. Okay, so now I plug into my formula, and I will say here, okay, so here that will be the 1 plus negative 2x squared plus negative 2y squared. And because I let y be a function of x, so I do dy dx first. So this is 0 to the 4 minus x squared, and 0 equal to 2. Okay, so now you will say, okay, so this one is 0 to 2, and this is 0 to what? 4 minus x squared, and this is 1 plus 4x squared plus 4y squared, dy dx is here. And then you think here, this is not really too easy to take integrations, right? Because you have dy inside here, it's not too easy. Then you say, maybe I can change to what? Maybe I can change to the polars, right? Okay, so if you change to the polars here, so as you can see, this is the circle, right? So the r is a constant. Not a constant, I mean the r has a fixed range. So I know the r is from the 0 to what? 0 to 2. And the same way, the theta, right? The theta is like in here. The theta is also what? Has a fixed ranges here. So this is theta is from 0 to what? Is a quarter, right? So it's a pi over 2 here. So I know this one, maybe if I change to the polar, will be a lot easier. Okay, so let's see here. So I know the polars here, right? So what is the x here? X is equal to what? R cosine theta. And what is the y here? Y equal to the R sine theta. Okay, so now let's take a look at this big mass here. All right, so this one's here, this is 1 plus 4x squared plus 4y squared. So this is 1 plus, and if you take the 4 outside, okay, so if you take the 4 outside, this will be the x squared plus what? Y squared, right? So what is the x squared plus y squared? It's r squared. It's beautiful, right? So it's 1 plus 4 r squared. So this whole thing can be, so if you put it into the square roots, so this whole thing can be changed to the 1 plus 4r squares here. Okay, so now let's take a look. How do I rewrite these integrations here, right? Okay, so we said I changed this one. So this one, this is 1 plus 4r squared. And also, if you guys remember, we said when we do the polar, what you need to times here? You need to times the Jacobians, right? So this is what we call it. This is a Jacobian for the transformation. And then we can do the, the integration. So in here, it doesn't matter. Both of them have a fixed, the fixed ranges here. So I can do just d theta dr. And what is the theta here? The theta is from 0 to what? Pi over 2. And what is the r's here? Is from 0 to 2. Okay, so like in here, so the first integration, there's no thetas here, right? So your data, so the integration, the r is a constant. So it will just be theta, and from the 0 to pi over 2 dr. So the theta is pi over 2, you can move the pi over 2's out, and then 0 to 2, and the r times 1 plus 4r squared dr's here, right? So what can you do here? Hey, man, I know how to do it, right? So you can, treat it, you do a u sub, right? So you can choose this one as a u sub. So then we use the u sub here. And so assume everybody know how to use the u sub. And finally, the answers here will be, this is pi over 24. So this is 1 plus 4r squared. And then this is 3/2. Then you put a 0, 2 inside. So it's going to be pretty close to the 9.044. So this is a good problem here because first we need to know how to set it up, right? So we need to know in here, you need to take a look by the Cartesian. You see here, it's very, very complicated. But then we immediately recognize, say, hey, this integration region is circular. So maybe the polar system will help us to simplify it. Okay. All right. So now let's take a look at the last problem here. So in here they say, hey, I'm trying to find the area of these triangles, right? This triangle at the vertices. So this is A, 2, 0, 0. This is B, and then this is C here. I'm going to find the area of this. So basically, you tell me I'm going to find the area of this triangle sitting in this plane, sitting in the R3s, right? So in order to do that, in order to use the formula, I need to know what is the, I need to know what is the equation of these planes, right? And then I can do the partial x, partial y's here, right? Okay, so now we take a look at these two. Okay, so the BA is here for this and A and CB, okay? So the BA and CB, okay? So these two vectors, right, they formed these planes here, correct? So I know, so that's why I know the BA, the cross product of the BA and the CB, what they determine here? So they determine what? Determined we call it is the normal vectors, right? to the surface here. Right, so it will be the normal vector. So now I know the BA, I can write it, this one will be 2, -2, 0. And also I can find the CBs here. The CB is 2, 0, -6. So let's do a cross product. So the cross product here will be what? Will be 12, 12, and 4. Okay? Okay, so now, you know, so 12, 12, 4, you can take out the 4. So this one here will just be the 3, 3, 1s here. So this is, you know, of course, you want to simplify. You can use 12, 12, 4, but you know, if you factor it out here, this factor is a lot easier to do the calculations, right? So so remember when we do the plan in the section, you know, in the previous, like in the vector space, so we need to have a normal vector and we need to have a point, right? So we say, okay, let me choose the 2, 0, 0, the point is here. So what is my plan? This yellow plan looks like. So the yellow plan will be the 3, the x minus 2, because I'm choosing the point 2, 0, 0s, right? So as a 3, the x minus 2 plus the 3y plus z equal to 0s, right? So I choose the point 2, 0, 0, right? So I have a normal vector, I have a point, and I can decide the planes here. So now for these planes here, so finally I can say 3x plus 3y plus z equal to 6. Cool? Okay, so now finally we can say 6 is z equal to the 6 minus 3x minus 3y. Finally, we have this function. And now what can we do? We can do a partial, right? Okay, so now let's say here, so rho 0 x over f of it, so it's -3, then rho 0 y equal to what? Equal to -3 here, right? Okay, so now, the area formula will be pretty easy. So I'm just do the integrations, and so it's 1 plus what? 1 plus -3 square plus -3 square dA. Okay, so now in here, I have this is 19, right? Okay, so this is region D, right? I have this is square root of the 19 dA. Okay, so I'm going to see where I'm going to integrating. I'm going to integrate y first, or I'm going to integrate x first, right? So if you take a look, if you get out, so this one's here, let me see which color I want. Okay. So the yellow is this triangle we try to find. And then I'm going to integrate out over these regions, right? So this region is bounded by this line, x equal to 2, y equal to 2. So you put it into the line equation with 2 points. You got this, so you got these lines, y equal to the 2x. Okay, so if you want to integrate it to the y first, you go this way, right? Okay, so let's try to write these ones here. So in here, I will say, okay, this is the square root of 19. I want to do dy. So y is from 0 to where? 2 minus x here, right? So it's 2 minus x and dx. So what is the dx? Dx is from 0 to what? 0 to 2. Okay, so now this integration is quite simple. This is 0 over 2, the square root of 19 to the y So 0, 2 minus x dx. So what you have here, you have 0 over 2 square roots of the 19, and the 2 minus x dx is here. Okay, I assume everybody know how to do these integrations. And so this one will be the square roots of the 19. And then this is a 2x minus x squared over 2. Then the limit is from 0 to 2. So we get this is 2 of the square roots of the 19 here. Okay, so this limit, so this problem is a pretty good problem. It's combining the several things. The first, that we need to know how to find these surfaces, right? So in order to find the surface, we need to know the normal vector. So what is the normal vector? We say, hey, we need to have the two vectors, they do a cross product. After you find the normal vector, then you find the point to find the surface. Then you apply the our area surface, the surface area formula, then be careful your integration regions, right? So you always, need to integrate out one variable first, and then make sure, is that variable is depends on the other variable or not. All right. Okay, that's it. So this is this section. Mechanically, I think it's a little hard, but concept-wise, it's pretty easy. It's very similar, like we talk about arc length. We are looking for the surface area, all right? So how do we apply the surface area? By using the tangent planes here. And so the same Renaissance concept. The real challenge is when you try to do the integrations inside that square roots, sometimes it's a little bit of challenge. And then sometimes you need to think about maybe you can switch to a different coordinates, and that might be help you. Okay, all right, that's it. And so I hope that you guys enjoyed these sections. Here is how to find the surface area. It's pretty interesting. Okay, I'm looking forward to talk to you. We're going to the next lecture. We're going to the triple integrations. Okay, all right. Have a good day, and looking forward to talk to you in our next video. Okay, bye.